Hello.
Hello.
Yeah. Can you hear me?
Yes.
Okay. So today onwards, we'll be starting counting problems in one of our classes in the week. So basically, this is a section where you will have problems where you have to count the number of ways in which something can happen. This is a major part of the syllabus. Like basically, five, six questions definitely like this you'll find in the AMC paper. So
Uh-huh.
we'll be working on these types of problems in one of the classes, and the other class will continue with number theory.
Yeah. Okay.
So the first problem here is how many ways are there? How many ways are there to rearrange the letters of a word when some letters are repeated? When some letters are repeated. A specific example could be if there are n letters in the word where x1 are letters of one kind, x2 are letters of another kind, and so on. Xn are letters of
Sorry.
a different kind.
Right.
Basically, these are different types of letters. The number of letters of each type is x1, x2 till xn, and the total number of letters is x1 plus x2 plus x3 so on till xn is equal to n. You have to find how many ways are there to rearrange the letters of this word under these restrictions. Basically, this is the general problem. An example of a particular case of it would be how many ways are there to rearrange the letters of the word sandwich, or say letters of the word synonym.
Okay. Yeah. So, the number of ways to rearrange a word in general, like if it didn't have any repeating letters, would be n factorial. So would this one just be like n factorial, like divided by how many repeating letters there are? So like x1 factorial, x2, and stuff like that.
Hmm. So if there is no repetition, you can rearrange it. All the letters can be rearranged in n factorial ways. But if
Yeah.
there is repetition, then there are x1 letters. Let's say there are x1 letters which are A. Then if you are just done n factorial, then you are considering each letter to be different. But actually the two A's are not different, or the x1 A's are not different, right? So you have to divide that by x1 factorial, because the total number is not going to be x n factorial anymore, right?
Yes.
So whenever you have some repetition of letters, each of the numbers, how many times each letter is repeated, that factorial you will have to divide by from the total number which was n factorial. This total number n factorial is the case where all the letters are assumed to be different, right?
Yes.
So this is the general thing. Now you have to solve the particular cases for these two words. You have to rearrange them and find how many ways to rearrange are there.
Okay, so for each one. Well, sandwich doesn't have any repeating letters, so it'll just be 8 factorial. And then synonym would be uh 7 factorial over 2
Why is
factorial.
uh-huh.
Huh? Oh, 2 factorial times 2 factorial again. So 7 factorial over 4. So 7
Hmm.
times 6 times 5 times 3 times 2 times 1. Um,
It's fine. You
30.
don't have to calculate it.
Yeah.
This is the answer for this. This is the answer for this one.
Yeah.
Okay. Then now second question is, a mathematical organization is producing a set of commemorative license plates. Each plate, each plate contains a sequence of 5 characters chosen from the contains a sequence of 5 characters chosen from the letters of AIME and the 4 digits in 2007. No character may appear in a sequence more times than it appears among the 4 letters in AIME or the 4 digits in 2007. That is a restriction. No character can appear more times than it appears in AIME or 2007. A set of plates in which each possible sequence appears exactly once contains n license plates. A set of plates where each possible sequence appears exactly once contains n license plates. Find n by 10.
Okay. So
Find the number of license plates you can make with these restrictions. When the license plate consists of a sequence of 5 characters taken from the letters of these and this.
would it be like 9 choose 5 divided by 10?
No. Getting a license plate is not just about choosing which letters appear. You have to arrange them in different orders.
Oh, right. So,
It's not like once you have chosen, that's it. You can make
yeah.
many different license plates out of those letters.
So, would it be you choose 5 characters and then you would multiply it by 5 factorial? Because that's like how many times you can arrange 5 characters.
That's one way you could do it, but that's not going to give you the correct answer direct because the characters can be repeated here.
Oh, yeah, they can be repeat. Okay. Uh,
Which characters can be repeated here?
Zeros.
How many times can zeros be put?
2 times. Oh, so you divide the entire thing by 2 factorial.
Is it guaranteed that every time you have to take two zeros?
No, that's also the same. So,
Is there any other letter that can be repeated?
um, mm, no,
So there
because
is one letter that can be repeated, which is zero. That can be repeated up to two times. How many cases are there?
in case 1, there's 0 is repeated, and then case 2 is 0 is not repeated. So 2.
What do you mean zero is repeated?
Oh, sorry. Well, one case is that there's 2 zeros, another case is that there's 1 0, and then one case is that there's no 0.
How many license plates can be made in each of these cases?
For no zeros, it would be 7 choose 5. No, sorry, 6 choose 5 because you have no zeros. In
Six
case
choose
2,
five.
yeah,
That's the
because
number
there's
of license plates.
no times 5 factorial because order. So then that just be yeah. So and then case 2 with 1 0, it would be so 1 0. So 7 choose 5 times 5 factorial.
That's wrong.
Wait, that's wrong. That's wrong because there's no guarantee that there's a 0 in it.
How is there no guarantee?
Oh,
We are
then
looking at this case.
yeah. So then you would do 6 choose 4 factorial to keep that 1 0 still there, and then that would be times 5 factorial. Okay, and then for case 3 with 2 zeros, you would have 6 choose 3 factorial. I mean 6 choose 3, and then that multiplied by 5 factorial, but then also divided by 2. Yeah.
What should we do now?
Um Now it says find n by 10. So
What should we do about the three cases? Now, what should I do?
you should simplify and then add them up. So then 6 choose 5 times 5 factorial is just 6 factorial. And then 6 choose 4 times 5 factorial. That's like 6 factorial times 5 by 2 factorial. And then 6 choose 3 times 5 factorial by 2 factorial. That's mm, that's like 6 factorial times 10 by 3 factorial. So then you have that 10 there, so you can just cancel out that 10 on top and then no, but it's adding. Never mind, never mind. Um don't you just have to calculate it out then, sort of?
Find the answer, and by 10 is being asked.
Yeah. Would it be 492?
No,
Maybe I did the calculation wrong because I got okay. I got 720 plus 1800 plus. Oh, that's where my mistake was. I did 20 times 120 instead of 10. Okay. So,
there is no 2 factorial here.
yeah, I didn't see that. I forgot to do it. So that would be one sec. So 372.
Yeah. Next question is, how many 4-digit positive integers have at least one digit that is a 2 or a 3?
Oh, Is the answer 5,416?
Hmm. How?
Well, I just did like there's 9,000 positive integers in total, so then I just did the number of positive integers that don't have a 2 or a 3. So that would be 7 times 8 times 8 times 8. So, and then I got 3, 5, 8, 4 don't have a 2 or 3. So then I just subtracted that from 9,000.
Okay, that's correct. Uh, how many ordered sequences of ones and threes sum to 16? For example, an ordered sequence that sums to 16 with ones and threes is this. Another ordered sequence would be these are two different ordered sequences of ones and threes that sum to 16.
Yeah.
You have to find how many such ways you can put ones and threes in a certain order to add up to 16.
Okay.
Remember, you have to calculate number of ordered sequences where it means that the order matters.
Yeah. Okay.
So the same sequence could have been written as 3, 1, 3, 3, 3, 3. And that's a different sequence. You have to count it separately.
Okay. I got 277.
Um,
So I did like cases. The first case is where it's just all ones. So then that's just one case. The second case is where it's all ones and then 1 3. So all ones and 1 3 means there's a total of 14 numbers because there'll be 13 ones and then 1 3. So then I did 14 factorial over 13 factorial because it's repeating. So that gets 14 different orders. So 14 different arrangements for that. Then I did 2 3s and the rest ones. So that's 12 numbers in total. So I did 12 factorial over 10 factorial for the repeating ones, and then 2 factorial for the repeating threes to get 66 arrangements there. And then I did 3 3s. I got 120 arrangements, 4 3s, 70 arrangements, 5 3s, 6 arrangements. So, and then I just added them all up.
Okay. Define the sum of a finite set of integers to be the sum of the elements of the set. Sum of the elements of the set. Now let D be the set of positive divisors of 700. Positive divisors of 700. You have to find how many non-empty subsets of D. Non-empty subsets of D have an even sum. What is the total number of divisors of this?
18.
And how many even divisors are there?
Oh,
Even divisors and odd divisors.
one sec.
Not so difficult to count even and odd divisors. For even divisors, you need the power of 2 to be what?
Oh, I got 12 even divisors. And you need the power of 2 to be 1 or more.
The number of even divisors is 12. The number of odd divisors is 6.
Yeah.
How can you get sum of the divisors is even?
When you have even plus even, uh, and odd plus odd.
You need to have an even number of
Even
odd
divisor.
factors, even number of odd divisors.
Right, yeah.
If you want the sum to be even, obviously we don't care about the number of even divisors.
Yeah,
For your subset of D, you need to have even number of odd divisors.
right.
So it could be 0, 2, 4, or 6, right?
Yeah, right.
0, 2, 4, or 6 odd divisors in your subset.
Yeah.
Do all the cases for these.
Okay.
We don't care about the number of even divisors in any case. If you select 0 odd divisors, after
Right.
that you can basically, in the case of 0 odd divisors, you can say that there is one way to select 0 odd divisors. Basically, don't select any of them.
Right, yeah.
What about the even divisors? How many ways are there to select?
Uh,
We don't care about the number of even divisors anymore in this case.
so 12?
No.
Is it just one? Because you can just choose all of them.
No. For each divisor, there are two choices, whether you select them or not select them.
Oh, so it's 2 to the power 12. Wait, no, that's not right. So for each one, you have two choices. So yeah, so it is 2 to the power 12.
You have 1 into 2 to the power 12, 2 to the power 12 ways to select the
Yeah.
divisors. If you select two odd divisors, how many ways will there be?
6 choose 2 times 2 to the power 12.
Similarly, you have 6 choose 4 times 2 power 12 and 6 choose 6 times 2 power 12.
Yeah.
If you add all of this, what is coming?
To well, yeah, you can take 2 to the 12 common. And then if you add all of them,
What is the sum of this?
Uh,
It is one half of the terms of the binomial expansion of power 6. You are excluding basically 6C1, 6C3, 6C5.
what?
What's the sum of these?
Um, 30. Oh wait, no, 620 is yeah, that's one. So 30.
Wrong. You are adding it also wrong. There is no need to actually do an addition. You can find out without actually calculating and adding. Why are you making mistake in simple addition? What is 6C2?
6C2 is 6 factorial over 2 factorial times 4 factorial. So 6 times 5 by 2 factor. So 3 times 15.
How is it 30?
Because 15 plus 15. And then, oh, and you add the 1. I didn't add the 1. So 32.
Why didn't you add the 1?
I think because in the past problems, we like multiplied them. I don't know. I just messed it up.
What is the sum of uh, even subscripts NC0, NC2 till NCN?
Mm,
What is this series going to add up to in general?
one half the sum of the entire thing.
What is the sum of the entire thing?
Like one half of NC0 plus NC1 plus NC2 plus NC3 all the way to NCN.
What is that sum?
Uh,
This is very standard information that everyone needs to know. How do you not know the sum of NC0 plus NC1 till NCN? What is binomial theorem?
it's like x plus y to the power n is equal to uh x1 y0 plus wait, sorry, x n minus 1 plus y0 times n c x plus uh
What you're saying right now. Right, tell me correctly binomial theorem.
binomial theorem, it's like when x plus y to the power n, so it's like nc, so you start off with the nc0 and then it's like x to the power
What's the
n,
first term? NC0 and what? What is here?
nc0 x to the power n, and then it's like plus nc1, and then it's like x to the power n minus 1, and then y to the power 1, and then you have like nc2, and then it's like x to the power n minus 2, and then y to the power 2, and then so on until it goes to like ncn, which is just like 1, and then y to the power n, because then you get x to the power n minus n, which is a 0. I mean 1, yeah.
So what is the value of NC0 plus NC1 till NCn?
uh just
Can we generate this series by looking at this binomial theorem expansion?
right. You can see the NC0, NC1, NC2 to NCN. So it's just XN plus XN minus, no, wait. So it's just like X plus Y to the power N divided by, wait, no, you can't do that because it's addition.
Put x is equal to y is equal to 1.
Oh, so if X is equal to Y, 1, that's just 2, oh, 2 to the power N
Is what?
is NCO plus NC1 plus NC2 all the way to NCN.
This is the first time you're seeing somebody say this. Put x is equal to y is equal to 1 in this.
I mean, I never thought about learned it like NCO, NC1, all that. Like the sum of it.
What is the sum of this now?
So then the sum of that would be 2 to the power n by 2. So 2 to the power n minus 1.
What's the sum of this?
2 to the power 6 minus 1, so 2 to the power 5. So 32.
These are the cases where we are getting an even sum. However, this case includes a situation where we selected 0 odd divisors and also we selected 0 even divisors, because when we do 2 power 12, we are giving every factor which is even an option to not be selected.
Yeah.
If you do no selection for every even and you have already selected zero odd divisor, then you're not selecting any divisor.
Right.
So that would be an empty set. So we are going to exclude that case.
Okay.
Basically, you're getting 2 power 17 minus 1.
Yeah.
If you do 2 power 17, that's the total number of ways, but that includes the empty set, where you have not selected any odd divisor and you also not selected any even divisor.
Yeah.
So the answer will be 2 power 17 minus 1.
Right.
Here we are focused on out of the even and odd divisors of 700, which ones we'll select and what we'll do about the other divisors. For each divisor, you have an option to either select it or not select it. We have
Yes.
divided the divisors into two types, odd and even, because we want to keep a handle on how many odd divisors we have.
Right.
Odd divisors cannot be odd because then the total sum would be not even.
Yeah.
So odd divisors cases are 0, 2, 4, 6. There are six of them. We have four cases. For even divisors, then we don't have any restrictions because we can select any number of even divisors.
Right. Yeah.
There are 12 of them. For each, you have a choice of either selecting or not selecting.
Right.
What are the total number of subsets of this?
Uh, 2 to the power 5, 6, 8.
So total number of subsets of this is 2 power 8 or 256.
Yeah.
We have to remove from there the subsets of these, right?
Right.
How many subsets are possible for each of them?
Uh, 2 to the power 5 for each.
So how will you calculate the number of subsets of this which are neither subsets of this nor subsets of this?
Mm, You'd subtract. So it'd be like 256 minus 64.
Wrong. You have to be careful.
Oh, wait, because 4, 5 is repeated in both. So, so 4, 4, 5, and 4, 5. So 64 minus 3. So it would be 256 minus 61.
No. You have to add back number of subsets of 4, 5. Why do we
Yeah.
have to add back?
Oh, because it's like counting it twice.
We are subtracting it twice. We have to add
Yeah.
it back once.
Yeah.
We still don't want subsets having 4, 5. We are just avoiding doing a double count. We don't want a double counting.
Right.
So you will say 256 minus 64 plus number of subsets of 4, 5, which is 4.
Right.
Answer will be 196.
Yeah.
Okay. We'll continue with counting problems in next week's class. Next class will be number theory. So
Okay.
we'll do some AMC problems on number theory in the next class. Practice counting problems from your previous year's AMC questions. You can also look at, you don't have to restrict yourself to AMC 10. You can start looking at AMC 12 papers also, because some of the harder questions in AMC 10 will be similar to your AMC 12.
Yeah.
So work with both the types of papers. AMC 12 also you should be attempting, because the difficult problems here will be similar to the problems here.
Okay. Yeah.
Practice questions from both, not just your AMC 10s.
Okay.
Okay, we'll continue on Thursday then.
All right. Thank you.
Hmm.
Bye.